Okay, so we're recording. So welcome everyone again to this new Graviticular seminar. Today the speaker is Jacinto Paulo Neto. He obtained his Bachelor of Physics in 2019 from the Federal University of Rio Grande do Norte, UFRN. Currently, he's a master's student and a member of the Particle and Astroparticle Group of the International Institute of Physics. Furthermore, he works on scientific dissemination of particles and astroparticle physics via the Particle and Astroparticle Teaching Group. So please, Jacinto, go ahead, and thank you very much for this opportunity.
Okay. Good afternoon, everyone. First, I thank you for the opportunity to present this work here. This work was developed in collaboration with Giorgio Arca, Farinaldo Queiroz, and Clarice Siqueira. This work is available on arXiv, and here we studied the dark matter phenomenology of a right-handed neutrino.
Something is wrong.
I thought it was me. I think maybe we lost Jacinto. Marcelo, do you hear me?
Yes, I hear you.
Okay, so it's not me.
I saw it was a problem with my internet, but no, it's a problem with Jacinto's internet.
Oops. Let me check. Oh, okay. So let's wait a couple of minutes to see if he's back. I'm going to pause the recording.
Let me see here. Okay, that's okay now?
Yes, perfect.
I'll just get back a little bit. Just to... Okay, so the outline of this work is basically, first I will give a bird's eye view of the work. Then I will talk a little bit more about the particle physics model and the non-standard early cosmological scenarios that we have considered in this work. Then I will bring the results and the conclusions that we have obtained from the dark matter phenomenology. Usually when we talk about the production of dark matter in the universe, we are talking about the fighting between the annihilation rate and the Hubble rate. The first is related to the particle properties of our dark matter candidate, while the second one is related to the cosmology environment, the cosmological background where this particle will evolve, and then at some point it decouples. In the part of our particle physics side, we use a type 1 to Higgs double model augmented by a abelian gauge symmetry, where we're gonna use the B minus L1. And also in this model, we have additional 3 right-handed neutrinos, where the first one will be our dark matter candidate. And also we have the additional scalar singlet. And in this structure, we have, and this gauge structure is given by the direct product between the standard model and this additional B minus L symmetry. In the cosmology side, we're gonna consider, for example, that dark matter will decouple during some early periods where the universe is expanding faster than the usual case, which is associated the usual with the radiation case, the standard case. And in this scenario, one of the fluids is very similar to a quintessence fluid, for example. And another background that we're gonna consider is that in the early universe, the universe was dominated by an unstable matter field. And we consider in this case 2 scenarios of dark matter freeze out. The first one is when the dark matter will decouple during the early period of radiation domination. And the second one is occurs when the dark matter decouples during the early matter domination due to this field. In the particle physics model, we have the particle content, which is very similar to the standard case, where, for example, in the quark sector, we have no change, we have no additional particles. And in the lepton sector, we have just the additional 3 right-handed neutrinos that I mentioned before. In the gauge sector, we're gonna have the introduction of the Z prime boson, which comes with the B-L symmetry. And in the scalar sector, we have the 2 Higgs doublets and the scalar singlet that I talked about. Here in the gauge sector, we're gonna have a mass mixing between the Z and the Z prime boson. In the brackets, we see the charges of the particles under each gauge symmetry, where we have here the SU3 color, SU2 left, hypercharge, and B-L symmetry. The Yukawa-Lagrangian of the model can be divided in 2 parts, where the first one we have the interactions between the scalars and the fermions of the standard model. And the second one, we have the interactions between these fermions of the standard model, for example, in this first term, and the scalars of the model. As one can see, the scalar singlet just interacts with the 3 right-handed neutrinos. And in this case, we see just the second doublet interacting with the fermions of the model, because we are considering the type 1 to Higgs double model, where in this case, we have used the criterion of natural flavor conservation to avoid neutral currents at flavor neutral currents at 3 level. And in this case, that will be basically somehow a very important role of the B-L symmetry here, which will be possible to make the mass matrices diagonal. And the generation of the neutrino masses will be given by, we're gonna need both terms, the Dirac mass and the Majorana mass, where in the first term, we don't have our dark matter candidate because it will be forbidden by a Z2 symmetry, because it will be odd under this symmetry in order to be stable. And so here in this term, we just have the second and the third right-handed neutrinos, but this term is already diagonal, and we have the 3 right-handed neutrinos here. Our dark matter candidate will acquire its mass after the spontaneous break of the B-L symmetry, and also when this field, when this scalar singlet develops its vacuum expectation value, it will also contribute to the Z prime mass via the kinetic term. And the other 2 right-handed neutrinos will be responsible for the generation of mass of the 2 active neutrinos, of the active neutrinos masses via the type 1 seesaw mechanism. The dark matter phenomenology is ruled by the neutral current Lagrangian given by this term. And here we have the B-L charge, which is 1/3 for the quarks, and for charged leptons, it is -1. It's I highlight that, for example, we have this symmetry doesn't see if the particle is right or left, the charge is the same for both. And also other relevant interactions for the dark matter phenomenology will be those interactions associated to gauge bosons and scalars, as for example, these 5 interactions. Now we move to study and try to understand what is this non-standard cosmology. So first I will just say what I mean for non-standard cosmology. Sometimes it's very misleading, and in the context that we studied, it means that in the very early beginning universe, before the time of Big Bang nucleosynthesis, the universe, in the standard case, we just considered that after the reheating of the inflaton, we just have the domination of the radiation. But now we're gonna consider different scenarios, and that's why we call it non-standard cosmologies. But it just means that we are changing the time of before the BBM. We have changed the cosmology, the cosmological scenario before BBM. First, let's consider, for example, that there was a scalar field in this epoch that makes the universe expand faster than radiation, and so this field is dominating. And at some temperature TF, a temperature of result, the dark matter decouples from the thermal bath and enters a relentless phase where the dark matter will try to get back to thermal equilibrium unsuccessfully. And at some temperature TR, the universe will start to be dominated by radiation, and now the freeze out will occur effectively. So there is no more this relentless phase where the dark matter is trying relentlessly get back to thermal equilibrium, and it is already annihilating its relic density. But this TR must occur before the time of BBM in order to save the process of BBM. We don't want any complications. The energy density of our field will be given by this equation, where the field will redshift as given here, and it must be larger than 0. Otherwise, we have the standard cosmology, the standard redshifting of the radiation. And in this case, when we make some algebras, we got some expression for this guy, and we can put it inside the freedom equation and obtain the Hubble rate given by this in terms of the TR and the N. And then we just put it inside the boson equation, and we can solve it, for example, for making some approximations to try to solve it analytically. And so if we assume that the annihilation rate is S wave, the annihilation cross section is S wave, and that this solution that will be obtained just can be applied to the region between the time of relentless, which happens after freeze out and before the time when the radiation starts to drive the expansion. We're gonna obtain these two solutions for n equal to. N equal to already sets the annihilation cross section as being S wave. And in this case, these solutions can be seen from this archive, where the researchers developed this model. And in this case, for these three fixed parameters, dark matter mass, TR, and the S annihilation rate, we're gonna obtain these behaviors. And as one can see, this dashed line, this dashed region, gives the relentless phase of dark matter. So it decouples at some temperature, at some time, in this case for this variable X, which is the inverse of temperature. So this decouples, and then it enters the relentless phase, as I said before, and at some TR, it will, or XR, the universe will be dominated by radiation, and the relentless phase stops. As one can see here, this relentless phase is translated in these equations as a logarithmic rate, for example, decreasing rate, for the case of n equal 2. And for the case of n larger than 2, we're going to have a power law decreasing in the Comalvin number density. As one see, for example, for radiation, we have the red curve, and for n equal 1, we have the green one. And here we don't see the relentless effects because it is not very present here. It is very similar to the standard case, but when the cross section is already S wave, we can see for n equal 2, we can see this relentless phase. And maybe it's important to highlight, for example, that for here we have fixed the temperature TR, but as n increases, we see that the freeze out happens earlier, and the Comalvin number density increases. And in this case, it is very similar to the cosmology, standard cosmology, but here it is like as it increases, it's similar to the decreasing in the cross section for the standard case. Another very okay, so the cosmological parameters we can fix here is the value of n, which is closely related to the cosmology background because it's closely related to the equation of state, and TR, which sets the time when the radiation starts to drive the expansion or the relentless phase stops. And so if we have, for example, freeze out fixed, temperature freeze out fixed, shorter, as smaller we have our TR, it means that the relentless phase was shorter. So since this period was shorter, it means that the Comalvin number density will be larger, right? And okay, it will be important when we got the results. For when we take x going to infinity, we can solve numerical the Comalvin number density, and when we put it inside this very common expression, we get the relic abundance in this case. Now, let's consider another scenario of in the early times where the universe has some matter period of domination. But first, we consider that the universe was driven by the expansion of the universe was driven by the radiation, and at some equilibrium temperature, the universe starts to be dominated by this unstable scalar field, which is a matter field because the parameter of equation of state. And so at some temperature, critical temperature, this field starts to decay, and it will end at the temperature Tn. That must be also that must be larger than the temperature of the BBN. See that we are considering here in the inverse of temperature, which is basically the x scale, even we are not considering the mass. Okay, this problem can be treated using the system of Boltzmann equations, where the S stands for the entropy of the scalar field, the entropy of the thermal bath, which will change because when this unstable scalar field decays, it will inject entropy in the thermal bath, since it will just decay into radiation. So this entropy will change after the decay of this field. Indeed, it will increase. And here, the capital gamma is the total the total decay rate of the scalar field. In this case, we consider two freeze-out scenarios. The first one, as I said, the very early of this presentation, we consider the radiation dominated freeze-out, where it will happen in this first radiation era. And for this case, we have the usual energy density for radiation. And when we put it in the freedom equation, we get this for the Hubble rate. And so to solve the Boltzmann equation, which is given which is very standard, it will give the approximately standard solution for the Comalvin number density. But now, in fact, we have to consider that at some late time, the scalar field will decay, and so the relic density of the dark matter candidate will be diluted due to this entropy injection. And so we have to define a dilution factor, which is given by the ratio between the entropy after the decay of the field and before. And this term will be always larger. And so we got, in terms of kappa and the dark matter mass and Tn. And so the approximate standard solution will be very similar to this case, sorry. The approximate standard solution will just take into account the dilution factor, and then we obtain the Comalvin number density today for dark matter and the evolution of the number density given by this expression, and the relic will be given by this one here. The cosmological parameters in this case will be kappa, which is the ratio between the energy density of this matter field and radiation at some scale of temperature mass. And here kappa must be very close to 1 in order to assure that at this time the radiation is dominating. So since we're going to consider in our results the dilution factor and Tn as our fixed parameters, we have to vary these guys in order to keep this kappa very close to 1, around 1. And also Tn, which will set the temperature that must be larger than the temperature of the type of the BBN. And so to ensure that the process in BBN will happen successfully, we have Tn must be larger than 4 MeV. The other case in this early matter domination is exactly, we consider that the dark matter particle decoupling during this matter domination, but before the time when this field decays. And we parameterize the Hubble rate as given here. And in this case, this parameter R must be between 0 and 1, so that it is given by the ratio between these energy densities at some scale of temperature T star. For R very smaller than 1, we have the case of matter domination at this scale. And for R very close to 1, the radiation will be dominating at this T star scale. The approximate solution for the Boltzmann equation, we have to consider R very smaller than 1 here, and so put it in the Boltzmann equation and solve it and so we're gonna obtain the Comalvin number density for the matter domination case. However, again, we have to consider the dilution factor because the injection of entropy. And in this case, we define, due to the parameterization, we define an inverse dilution factor, which is given by the ratio between the entropy before and after the decay of this field. So the Comalvin number density will be given by, will take also into account this zeta parameter, which is our inverse dilution factor. And the relic density will be given by this expression here. So the cosmological parameters that we're gonna consider, that we're gonna fix it, will be zeta and T star, which is the temperature scale. Okay, now we are moving to finally to the results. And first, I will just explain a little bit of this parameter space where we have the dark matter mass versus the Z prime mass. And here, for each of these figures, we have different cosmologies, as I said before. In this case, for the standard, for the faster than usual Euler expansion, we have n equal 2, n equal 4, and n equal 6. And so it makes different scenarios where the dark matter will decouple, sorry. And here, the shaded region gives the bounds of the models, the bounds on the models that we have put. And DD means direct detection. APV means atomic parity violation. And Z goes into D jets for collider physics, and also D leptons for also collider physics. Here it means flavor physics and unitarity on a theoretical bound. Here we also have fixed the value of the coupling of the B minus L symmetry to 1. And these contours here, the colorful ones, and also this black one is the right relic density in this parameter space, where in this case, this black contour is the standard case of radiation. So we have considered, for example, we just take the model and use the standard cosmology and obtain this relic abundance today. And this color, this red, blue, and brown will be the right relic abundance for n equal 2 cosmology, but different temperatures, TR, I mean, the temperature of the end when the relentless phase ends. Okay. We see that when we decrease for a fixed cosmology, when we decrease the value of the TR, we're gonna need larger cross sections in order to suppress the enhancement of this relic abundance. As I said before, when we decrease the value of TR, the relentless phase will be smaller, so that it will give larger Comoving number densities. And the same happens for different values of n. As one can see, it will give always larger cross sections, because as I increase the value of n, I will get larger and larger enhancements to the relic abundance. And so we see that the contours will move towards smaller Z prime mass, which is the same as saying that it's larger cross sections, and in order to suppress these enhancements on the DM relic density. On the other hand, if we take, for example, here, fixed value of TR, we're gonna have that the larger the dark matter mass, we're gonna have larger Z prime mass. But why is it happen? It happens because, as in the standard case, the larger the dark matter mass, the early will be the result of this particle. So in this case, for a fixed temperature TR, I mean the end of the relentless phase, it means that we're gonna have longer relentless phase, and longer relentless phase means a decreasing in the Comoving number density. So I will need smaller cross section in this case. Okay, now we're gonna discuss about the results in the case of early matter domination that we have considered, as I said, two different results epochs. And in this case, we also have fixed the value of the coupling equal 1. And the primary space, of course, is the same as well as the bounds. And here, for the case of radiation, we have set the value of the dilution factor equal for the smallest value for the kappa around 1, and the largest value for kappa around the value of 1 to ensure that is happening during the radiation domination. And here, as one can see, the larger the entropy after the decay of the field, the smaller will be the cross section, and also the lighter will be the dark matter mass needed to be free from the bounds. That's what I mean for lighter dark matter mass required. And here we also compare it to the standard case, of course, because it's basically, as we can see, it's moving. It's like if I have an universe that is expanding very faster, this contour is moving toward toward the left side, and it means for smaller. It means it is going to smaller z prime masses, larger cross sections. While in the case of when we consider that the expansion is lower, it will goes to the right side of the panel, and in this case it will require just smaller cross sections. Here, as one can see, this magenta contour gives the smallest inverse dilution factor, which means basically that the entropy after the decay of the field is larger, as well as happened in this case. So it's okay. And in this case, we can compare both cases, and we see that the entropy after the decay must be larger for the case of matter result, matter dominated result. Here we have said these also are the parameters that we must have, the largest and the smallest in terms of the inverse dilution factor. And this one is the smallest value of T star, and the largest one is this magenta one, because we have to assure that the other temperature of result, temperature of reheat, temperature of reheat, the temperature when the BBM occurs, this Tn must be occurs must be larger than the temperature of the BBM. So these are the values that we can have, in the boundaries of the primary space, cosmological primary space. Okay, now we move to conclusions. The conclusions of this dark matter phenomenology associated to the computation of the right relic density of dark matter today for our dark matter candidate, which is a right-handed neutrino. And we have explored the impact of different non-standard cosmologies on the right-handed neutrino, which is encompassed in a two-Higgs double model, and in additional, the -L gauge symmetry. We have considered the relentless result, which is the case where the universe was expanding faster than radiation. And we also consider in the case of the existence of a matter field that dominates in the early universe, we consider radiation dominated result and matter dominated result. And when we see the result for faster expanding, we see that we need very large cross sections, and it will be very bounded due to the constraints. And so it maybe this kind of cosmology should not exist if our dark matter candidate exists. For the early radiation dominated and for the case of early matter dominated results, we have that in the first case of radiation, dark matter mass around 200 GeVs will be already constrained from the bounds. And for the case of matter domination, nearly 400 GeV is already enough to be completely unconstrained from the bounds. That's all. Thank you again.
Thanks, Jacinto, for the very nice talk. It was very, very good. So is anyone have a question for Jacinto? Maybe not. Jacinto, you mentioned that you are publishing this work? You are publishing this work or not?
Yes, we have already submitted on archive.
Okay,
and now
excellent.
We have submitted in this review D. We are waiting.
Cool. And do you know what are your next next steps for this study? I mean, for example, I was wondering if you're planning on, I don't know, I'm just asking this from ignorance, if there is any real data from some experiment that you can compare with, how does the model look there? Do you plan on doing something like that?
In terms of which kind of experiments?
I mean, connecting the model with some experimental data. If there is, I'm not sure.
Yeah, indeed. In the bounds here. Just a moment. Yeah, okay. These bounds are related to the experimental research. So, for example, here we have a commutative violation bound, which is related to the parity violation in the atomic scattering between the dark matter mass and some experiments nucleus. And here the collider research is about the existence of a Z prime mass, which could, for example, which could constrain our dark matter candidate, and also flavor physics and direct detection, which is very, in this case, the stronger bound, the stronger constraint will be the associated to the spin dependent cross section. So we have all these bounds, unless this unitarity, which is related to theoretical bounds, we have considered. But for next work, we are thinking, for example, to study the particle properties of this scalar field, because as you have seen, I have not talked about the particle properties of this field. So one very exciting research could be related to this part, for example, because we have many scalars in our model, and maybe, I don't know, but maybe we could, for example, introduce some kind of another, or could be, I don't know now, because we have not yet seen everything, but could be, for example, this scalar singlet or something like this, and what could happen if we have properties, but it's harder to do, so it will be the next.
Okay, good. And I'm just wondering, just being curious, this, for example, collider physics experimental bounds, do you know which experiments are involved there?
In this case, we take, for example, how can I say, interactions between leptons, for example, here, the D leptons, jets, and here we search, for example, in terms of statistical, and also watching in the case of the numbers of events, in the bumps, in the LHC, for example, and other experimental collider research. So we basically are trying to see some kind of asymmetry of this Z prime boson. That could be, of course, another kind of model that's not necessarily related to mine, but it's already something.
Okay, good. Is there any other question? Okay, I think there is not.
Okay.
Ah, Marcelo?
No, I wanted just to thank. Do you have any comment about this tension that we have in connection with the Hubble constant? Your model can say something about this point, or not?
Okay, you say the Hubble tension related to the measurements in the closed universe, closer. I mean, for the what can I say? In terms of distance, and also in terms of the Hubble computed from the CMB. And yeah, we have some tensions, but we can, for example, Farinaldo have just at some, I think last year, I don't remember exactly, but have submitted on archive a paper where he was trying to solve this problem using a dark matter model, a dark matter particle. And maybe we can, for example, reconcile the Hubble tension. We can also reconcile the problem of lithium, for example, and the dark matter problem. So sometimes in the case of the Hubble tension, I would say that's just it may be just in terms of our theoretical meaning that is missing to understand, and or some observational features that must be, what can I say, some fine-tunes. And so we have to see that, but I don't know how to say too much about it.
Okay, thanks a lot.
Claudio, do you have a question or comment?
Yes, maybe I missed this, but is there any way to get indirect detection of this dark matter?
Yeah, I see. So in this case, our model did not accomplish for indirect detection. In this case, we have no bounds on the indirect detection because some problems that I didn't see exactly, but we have not considered in this case. I can't explain clearly.
Yeah, for example, like if you had some annihilation into, photons or something that causes.
Yeah, exactly.
Right.
But there's some point that I'm missing.
Okay. Thank you.
Nice, thank you.
Okay, good. So is there any other question or comment? I think not. Okay, Jacinto, then thank you very much for giving this talk, this seminar, and I hope to see you all next Thursday. Okay, bye-bye.
Sure.
Have a nice day.
Nice. Bye-bye.
Bye-bye.
Okay. Thank you.